In fact, I remember so well that this scene that stuck with me when I was preparing this lecture. All right, so I was in Wheaton Library. I saw the movie in passing. I'm thinking, wait a minute, I was a little kid. What did I know? I didn't have any sophisticated understanding of science. You know, you're kind of like a Disney type of person at that point. So I'm thinking, wait a minute, let me go watch the movie again. This time, I figured that I would enjoy it. You know, I'm a physicist, right? Again, it was the same thing. Oh my God, I could not tolerate the movie. I just tried to watch it. It wasn't going anywhere. I said, okay, this is the scene that I wanted to grab. I grabbed it. Just so that you guys know what I'm talking about. Scene that I'm just. This scene is almost 5 minutes long. I'm not going to bore you with a 5 minute of this scene. So I'm going to cut it to the next scene. And then you're on the inside. So that thing is spinning. So it's generating acceleration on this wall towards the center. Obviously, if you're on that wall, you're going to feel it pushing the opposite direction. And now you're going to watch this guy jog for 5 minutes. All right, so this movie is a classic. Now, if you're going to be spinning this thing in space in order to generate artificial gravity, right? Why not spin it at 2Gs or 3Gs? What would happen to you if you experience acceleration at 3Gs for 6 months?
When you get back to Earth, you're going to feel super light.
Or you're going to feel much stronger, right? In a sense, it's kind of weird. Yeah, when you get back to Earth, you're going to be much more muscular, in essence. Right, it's an example problem. Let's take a look at problem number 9. Let's take a look at problem number 9. This is the one I want to look at, so I'm just going to skip that one. I want to skip this. This is not edited. Yeah, probably. Okay. It's a fast edit. I need to edit it again. All right. So what we have? It's straightforward. This is not going to be part of the problem set unless I have a multiple choice math section of the test ready, which I don't intend to this week. All right. So what do we have? We got a space shuttle orbiting the Earth. Evidently, it's 400 kilometers from the surface of the Earth. So I'm going to end up using the letter D for the distance for this case. All right. So that's the selection that I made. So this time it's expressed in terms of kilometers. So this is a big problem. I didn't really modify it. So each revolution is going to take 90 minutes. That's what it means. So it's going to circle the Earth about every 90 minutes. So each revolution takes 90 minutes. So what's the centripetal acceleration? So that's what we want to know. The kilometers to meters. 1 kilometer is going to be 1,000 meters, in case you didn't know. Minutes to seconds. 5,400 seconds is fine. All right, now a couple of things we need to do. All right, the radius of the Earth is something that you will look up normally, and because I used this so many times, I actually memorized it. So that's the number. And what else do we need? Okay, now we want the actual radius of the motion all the way to the space shuttle. All right, so we need this lowercase r. So lowercase r is going to be capital R plus d. And then just add up those two numbers. Okay, and this, don't forget, this thing is moving. So it gives you this number. Okay, so how do you do a problem like this? Okay, I'm going to introduce something that we will get to use quite a bit in the future. If you take physics 2 with me, this thing is also going to come up quite a bit. Okay.
Are you going to take it next semester?
Yeah. I mean, I do physics 1, physics 2, and also physics 3 if they're offering it over the summer. So if you like my style, just stay with me. So, so what do we know? What do we know? So we got r. So this is the radial distance. We are looking for the acceleration, centripetal acceleration. So the question is, v is not given, right? So how do we do v? Okay, so I'm going to show you a trick. This is going to help you in the future, even if you take it with someone else. V is distance over time, right? So the measured distance over measured time. Okay, so measured distance that it's traveling is the circumference of the circle, right? So that's your measured distance. And it takes you 90 minutes to actually go around. So each cycle that you're looking at, each round that you're looking at is going to take 90 minutes, right? So from that information, now you can figure it out because circumference is going to be 2 pi r, and r is this lowercase r, divided by the time it takes for you to actually complete this cycle. So that's known as the period of this motion. So circumference divided by the time is going to give you the speed in essence. Okay, so that's what we will do. So I say, yeah, let's figure out the speed first. So it's going to be the circumference of the motion divided by the time it takes for you to complete that cycle. So circumference is 2 pi r. So I'll do a back substitution. Change my mind. All right, so 2 pi r divided by t is going to be v. And then we'll just do a back substitution there. All right, so that expression squared divided by r. And then I'm struggling there because it's late at night. All right, so you got an r squared, you got r. So obviously that's the only cancellation you will have. Boom, boom, boom. And I forgot the square. Somebody's going to tell me that. Okay, now this one magically appears. And then the numbers, you get a number from someone. This number is ridiculously high, so this is no good. and somebody's going to give me a better number. Okay, now this makes sense. Okay, so it's going to be less than a G. All right, so for us, it's the surface of the Earth is going to be 9.8. If that day where the space shuttle is, it's 9.2 almost. So it's like 9/10 of a G. So the question is why? All right, so that's as far as we will go with this portion of the lecture. So we finish up. Okay, so